Now that we have completely settled and resolved the issue of stationary distributions for irreducible Markov chains, we have developed the theory, we have given the theoretical results, we have also studied some examples which gives you ideas about the techniques, etc. In this module, we are going to actually turn into a slightly different question, which was raised earlier in connection with a two-state Markov chain, namely, how about limiting distribution for such a chain? In other words, what we're going to look at is, we consider still an irreducible Markov chain and ask, is there a limiting distribution? So what we are going to do to answer this question is, we will see somehow another important concept comes into play, namely that of periodicity. So we'll explain the notion of periodicity, and then there would be something called aperiodic chains, and for aperiodic, irreducible, positive recurrent Markov chains, we are going to prove a very, very important theorem known as the ergodic theorem for Markov chains, which is one of the most important and useful theorems for Markov chains, which will give really a result on limiting distributions. And then we'll have some analogues also for other cases. For irreducible positive recurrent, but not necessarily aperiodic, also we'll get some results. So let's quickly start by recapitulating what we know already. We know that for an irreducible Markov chain, firstly, either all states are transient. There are three possibilities. Or all states are null recurrent, or all states are positive recurrent. That's the first thing. Next, in the first two cases, that is, if all states are transient or null recurrent, no stationary distribution exists. In the last case, the Markov chain has a unique stationary distribution pi, and in fact, pi is given by this formula, that is, for any x in S, pi x is the reciprocal of the expected return time to x starting from x. So far as stationary distribution is concerned, this is the situation for an irreducible Markov chain. We'll come to non-irreducible Markov chains later, but this is the situation as far as, so we've completely solved the issue of existence, uniqueness, etc. of stationary distribution for at least irreducible Markov chain. But we're going to turn to a new question now, something that we've encountered before and mentioned before. When does a Markov chain have a limiting distribution? See, limiting distribution is different from stationary distribution in general, at least idea-wise. So to be precise, if mu is the initial distribution of the Markov chain, then of course the distribution of xn for each n would be given by, so we call it p mu probability. So p mu probability that xn equal to y is given by this. We have seen this before. So you condition on where the Markov chain started from. So conditional probability that xn equal to y given x0 equal to x, but then you have to multiply with the probability that x0 equal to x, and that's where mu x comes into play. So that's a theorem of total probability. So the question is, does this p mu distribution of xn, namely the probability that p mu xn equal to y, does it converge to some mu y infinity as n goes to infinity, where mu infinity represents some probability on S? That would, if that happens, then we would say that the Markov chain does have a limiting distribution under the initial distribution mu, and the limiting distribution is given by mu y infinity. So as I said, such a mu infinity would then be limiting distribution of xn under p mu. Of course, mu infinity should be and is allowed to depend on mu in general. So this is a question we are going to ask, and as we have done so far, for stationary distribution also we restricted ourselves to irreducible Markov chains. So first we'll try to answer this question completely for irreducible Markov chains. So therefore we are going to study limiting distributions for irreducible Markov chains. So first we quickly want to make an easy claim. If all states are transient or all states are null recurrent, remember that in irreducible Markov chain there are only three cases, three contingencies that are possible. Either all states are transient, or all states are null recurrent, or all states are positive recurrent. Now what I'm saying here is that in the first two cases, no limiting distribution exists, whatever be the initial distribution. Why is that so? Well, that's because in both cases we know that limit as n goes to infinity of this sum 1 over n, or this average sort of 1 over n k equal to 1 to n, pxyk is, the limit is 0 for all xy in S. We know that. We have seen that before. In fact, this is something that was observed when we also show that for these two cases there cannot be any stationary distribution. Now what we want to say is that because this quantity 1 over n summation k equal to 1 to n pxy super k in absolute value is less than or equal to 1 for every xy, because each pxyk is a quantity less than or equal to 1. So if you take the average of these things, then also the average is less than or equal to 1. So then therefore you can use the dominated convergence theorem to conclude that as n goes to infinity, the limit of 1 over n k equal to 1 to n summation over x mu x pxyk will be 0 for every y in S, whatever be the probability mu on S. So you can convince yourself that that would be a consequence of the dominated convergence theorem. Now we want to show why is it that no limiting distribution can exist. If there is the limiting distribution mu infinity, that means limit n p sub mu of xn equal to y, we are calling it mu infinity y, if such a thing exists. Since this sequence p mu xn equal to y as n goes to infinity converges to mu y infinity, the average of this sequence also will converge to the same limit. That's a standard fact in calculus. If a sequence an converges to some limit a, then 1 over n summation k equal to 1 to n ak, that average also converges to the same limit a. But we already have seen that the average converges to 0. Therefore this would force that mu infinity y has to be 0 for all y in S. So there is no issue about, no question, no possibility of there being a limiting distribution. So just like before we saw that in a transient or null-recurrent case for an irreducible Markov chain there are no stationary distributions, likewise there are no limiting distributions either. So therefore the only other case that remains is, if the states are positive recurrence, then what? Do we have a limiting distribution? Now of course in this case we know that there is a unique stationary distribution pi such that at least the average is 1 over n k equal to 1 to n pxyk, the averages converge to pi y for all xy in S. Using dominated convergence theorem exactly as above, you can easily verify that if you now take any initial distribution mu on S, then still the averages have to converge to the same limit pi y for every y in S. It's again a consequence of dominated convergence theorem. If xn is an irreducible Markov chain with positive recurrent states, and if pi denotes the unique stationary distribution, then limit n 1 over n k equal to 1 to n p mu probability that xk equal to y, that limit also is pi y for all y in S, whatever be the initial distribution mu. So if this limit exists for any initial distribution mu, suppose such a limit exists, then the average of this this sequence p mu xn equal to y would also have to have the same limit, which means that mu infinity y has to be the same as pi y. So the upshot is that whenever a p mu limiting distribution exists, it has to be the unique stationary distribution pi, whatever be mu. So the question of whether a limiting distribution exists or not is a different question. We haven't answered that. But what we have seen is, if for some initial distribution mu, a p mu limiting distribution exists, then that p mu limiting distribution can't be anything else but the stationary distribution pi. So in view of this, the question of whether limiting distribution exists or not becomes the same as asking, because the previous this fact really tells you a limiting distribution, if it exists, does not depend on the initial distribution. It will be the same whatever the initial distribution. So therefore asking the question of whether limiting distribution exists or not becomes the same as asking this: for an irreducible positive recurrent Markov chain, does p mu xn equal to y converge to pi y whatever be mu? Now by virtue of DCT, it is not difficult to see that this is equivalent to the simpler question. I don't have to bring in any initial distribution mu. For an irreducible positive recurrent Markov chain, is it true that pxyn goes to pi y as n goes to infinity for every x and y in S? You can verify that by DCT. This answer to this question is equivalent to getting an answer to the previous question. Now we know that average of the pxyns, that sequence, the average sequence converges to pi y as n goes to infinity. But what we are asking for is, does the sequence itself, pxyn, does the sequence itself converge to pi y, which of course is a stronger state, because in general we know in calculus that if a sequence converges to a limit a, then the averages of the sequence also converge to the same limit, but the other way is not true, the other way around, in general not true. So here we know the averages converge. So from that statement, the statement that the sequence converges would be a much stronger statement. And matter of fact is that the latter does not hold in general. So here's an example. Consider this irreducible finite state space and therefore positive recurrent Markov chain with 3 states given by this. Now if pi denotes its stationary distribution, then clearly pi x is positive for every x in S, as we have seen before. Now our claim is that, in particular, for example, Pxxn, if you take any x in S, which is 3 states, Pxxn does not exist, which would say that you cannot have a limiting distribution. Because if it did, then the limit has to equal pi x, which is positive. But it should be clear that if n is odd, then Pxxn is 0 for every odd n, because you cannot go from x to x at all in an odd number of steps. That's because of the very structure of the transition probabilities. Now you can similarly recall the Ehrenfest diffusion model with this state space and these transition probabilities. You see that Pxyn is 0 for all odd n if y minus x is even, and 0 for all even n if y minus x is odd. And therefore, arguing exactly as in the previous example, you can conclude that limit n Pxyn does not exist for any xy in S. So therefore, here are 2 examples of irreducible finite state space Markov chains in which there are no limiting distribution, even though there is a stationary distribution. Now what is it that is happening in these 2 examples? Why did we look at these 2 examples? So you will see, if you think about these 2 examples a little bit closely, you will see that the common feature in the 2 examples is that in both cases the evolution has an underlying periodicity. Now let me explain what that means. In the first example, the chain can move from any state x only to one of the other 2 states in the next step, so that it always needs an even number of steps to come back to x. So that's what I mean by a certain underlying periodicity. In the second case, the second example, the Ehrenfest diffusion model, starting from any state x, the chain can only be in x plus minus 1 in the next. So that to move from x to y, the chain would need an even, respectively odd number of steps, depending on whether y minus 1 is even or respectively odd. So this is what I mean by periodicity. And it is the periodicity, this common feature of periodicity in the 2 examples that we have seen, which actually prevents a limiting distribution from existing, even though stationary distribution exists. What we are going to see that in general, it is only such periodicity that prevents Pxy super n to go to pi y for all xy to hold. So now we want to make that idea of periodicity, etc., a little bit more precise. So I come back to any Markov chain. Suppose x is a state such that x leads to x. That means starting from x, the Markov chain has a positive probability of going to x, returning to x in a finite number of steps for some n. So if x is such a state, then for such a state the period of the state x is defined as, you look at all the n's such that Pxxn is positive. So you know that this set is not empty because we are assuming that x leads to x. So there is at least some one n for which Pxxn is positive. So look at the set of all such n's, and it's the greatest common divisor GCD of this set of n's that is defined as a period of dx. So the definition would definitely mean that any n for which Pxxn is positive has to be a multiple of dx, because dx is supposed to be the GCD of a set of n's. So Pxxn is positive only if, but of course not necessarily if dx divides n and dx is the greatest positive integer with this property. Okay, so this is the definition of period of a state x modulo that condition x is such a state which leads to itself. So here is the proposition. If you have an irreducible Markov chain, then period is defined for all states and is the same for all of them. Why is it so? Firstly, by irreducibility, for all states in x, x will lead to x. So dx is defined. Now I want to show that any 2 states have the same period. So let x and y be 2 states Because x leads to y leads to x, remember irreducibility. So there are integers n1, n2 such that pxy n1 is positive, pxyx n2 is positive. By the Chapman-Konogo equations, the CK equations, you can easily see that pxx n1 plus n2, the probability of going from x to x in n1 plus n2 many steps, is certainly greater than or equal to the probability of going from x to y in n1 steps, following it up with the probability of going from y to x in n2 many steps, because this is one of the many different ways in which the chain can go from x to x in n1 plus n2 many steps. So therefore this is positive. Now if Pyn is positive for any n, for some n, then by the same argument you can see that Pxx, again Chapman-Kolmogorov equations, n1 plus n2 is again positive because of the same reason. Now by definition of dx, the above will imply that if dx divides n1 plus n2 and dx divides also n1 plus n plus n2, because pxx from n1 plus n2 is positive, so dx divides n1 plus n2. Pxx n1 plus n plus n2 also is positive, so dx divides n1 plus n plus n2. But then dx must divide the difference, which means dx divides n. And this holds for any n with Pyn is positive. What does it mean? That means dx dy, which is the density of all such n, has to be a multiple of dx. Of course, reversing the roles of x and y, you can easily see that dy also divides dx, so dx equal to dy. So what we have proved is that in an irreducible Markov chain, every state has a period, and the periods are actually all same for all the states. So we can call it the period of the chain itself, and that's what this definition says. For an irreducible Markov chain, the common period of all the states is called the period of the Markov chain. Now comes the next definition. An irreducible Markov chain is called aperiodic if the common period is 1, while it is said to be d-periodic if the common period is some d greater than 1. So what is our goal? I mean, why did we bring up all these things? Goal is that we are going to show that if you have an irreducible aperiodic positive recurrent MC, it's sometimes called an ergodic Markov chain, then limit n pxy n exists is equal to pi y for all xy n in S, where pi is the unique stationary distribution, and as a consequence the chain has a unique limiting distribution which is pi, whatever be the initial distribution mu. So apart from positive recurrence and irreducibility, we need this extra condition of aperiodicity. So remember, we discussed and we sort of claimed that for the two examples that we gave in the beginning, it is a periodicity feature that prevents a limiting distribution from existing. And what we are just about to show is that it's just that periodicity which prevents. If there is no periodicity, then there is a limiting distribution. So to prove this, we need a simple fact from algebra. So let A be a non-empty subset of natural numbers with the property that if any two natural numbers belong to A, then their sum also belongs to A. Claim is if D is the GCD of A, then there exists some n naught such that every multiple of D, every nd for n greater than or equal to n naught belongs to A. That means after some stage, all multiples of D are elements of A. Since this is a fact from algebra, I'll just give a sketch of the proof. Enough to consider the case when D is 1, because otherwise you can replace A by, you take all the elements of A, divide by D, you get a new set which would have the property that if m plus n is A, then m and n are in A, then m plus n is in A, and of course 1 would be the GCD of this resulting set. We are considering this case that when D is 1. Now, starting with the set A with the given property that m n in A means that m plus n is also in A and 1 is the GCD of A, define this set of integers G. Remember, A is a subset of natural numbers, but G is going to be a subset of integers. G is all numbers of the form km plus lm prime, lm tilde, where you take m and m tilde from A, and k and l are any integers, positive, negative, 0, whatever. Then you can easily see that G is a subgroup of the group of integers, and you can also see that clearly A is a subset of G, because you can always take for any m in A, you can take k to be 1, l to be 0, then m is in G. So let R be the smallest positive integer in the group G, in the subgroup G. Now for any m in A, if we write m equal to qr plus l, this is the Euclidean algorithm. So you take m divided by r, q is the quotient, l is the remainder. Then L equals m minus qr is in G. Why? Because m is in A, therefore in G. R is the smallest positive integer in G, but in particular R is in G, therefore qr is also in G. So m minus qr is in G because G is a group. But that implies that L is 0. Why? Because L is supposed to be strictly smaller than R and positive and non-negative. So if L is positive, then L would have been a positive number strictly smaller than R, which belongs to G. But that's impossible because R is chosen to be the smallest positive integer in G. So the only thing that's possible is L is 0, which means that R divides. So that means that if you take this R as we defined, it divides every m in A. But then GCD of A has been assumed to be 1, so that means R is 1. But if the smallest positive integer in G is 1, that means if 1 belongs to G, G is a group, that means G is the set of all integers. But not only that, it means that m minus m tilde equal to 1 for some m and m tilde in A. Why is that so? Because in general, if you take the GCD, if you take R, which is 1, is in G, remember that any element of G is obtained as km plus lm tilde, where k and l are elements of Z and m and m tilde are in A. But if m is in A, k is in a positive integer, then km is in A, and so on. So from that you can deduce this. Now you can take n0 to be this particular number, and with a little bit of algebra you should be able to show that this n0 works. So that details I am leaving out. So now comes one of the major theorems, most important theorems in Markov chain theory. So this particular lemma that we have just now proved, if you apply it to an irreducible Markov chain with period d greater than or equal to 1, that tells you that for every x in S, there is an n naught depending on x such that pxx nd is positive for every n greater than or equal to n naughts. That's just an immediate application of the lemma. Now we are about to prove, as I said, this so-called ergodic theorem for irreducible Markov chain, which is, as I said, is one of the most important results in Markov chain theory. It says for any irreducible aperiodic positive recurrent Markov chain with its unique stationary distribution denoted by pi, limit pxy super n as n goes to infinity is actually pi y for all xy in S. Of course, as you have seen, in particular this would imply that such a Markov chain has a limiting distribution no matter what the initial distribution is, and that the limiting distribution is actually unique irrespective of the initial distribution, and the limiting distribution is indeed pi y. Okay, so first claim, for all xy in S there exists an nxy depending on x and y, an integer greater than or equal to 1, such that for all n greater than or equal to nxy, pxy super n is positive. So this is just an application of the lemma and basic facts about this Markov chain being irreducible, etc. So this is why that is true. Now I'm going to do something which is very special. So you consider you are starting with a Markov chain xn with state space S. We are going to consider a Markov chain with state space which is a Cartesian product of S cross S. So I'm going to consider a Markov chain, I'm going to call it xn bar, which would be are denoted by xn comma xn tilde, 2 coordinates. State space is S cross S. And the transition probabilities are given by this. P bar of xx tilde to yy tilde is P of xy times P of x tilde y tilde. So if you look at it, essentially xn and xn tilde represent 2 independent copies of the original Markov chain. Both xn and xn bar, xn tilde running according to the original transition probabilities. They are running on S as state space with the original transition probabilities, and xn bar looks at the joint evolution of the pair of these 2 independent Markov chains. Claim is this new xn bar is also an irreducible aperiodic positive recurrent Markov chain. That is a property that the original Markov chain had. Now from the definition one can see that if you take any xx tilde and yy tilde in S cross S and any n greater than or equal to 1, then P bar of n of xx tilde comma yy tilde equals by definition Puxin times Px tilde y tilde n. The best way to see this is because if you just think of xn and xn tilde as being 2 independent Markov chains running parallelly, then the probability that the paired Markov chain xn bar reaches yy tilde, state yy tilde in n steps starting from xx tilde, that amounts to the one of the 2 chains, xn chain, going from x to y in n steps, and at the same time the second chain, the xn tilde chain, going from x tilde to y tilde in n many steps. And since it happened independently, so it's the same as the product, and that is positive for all n greater than or equal to maximum of nxy and n x tilde y tilde by the definition of nxy and x tilde y tilde. So this proves at one go both irreducibility as well as aperiodicity of xn bar. Next, it is easy to see that I'm going to define a probability pi bar on S cross S, which is defined as pi bar of xx tilde is pi of x into pi of x tilde. You can easily show that this is a probability on S cross S, and this is actually stationary distribution for xn bar. So this will show that for this xn bar chain I have exhibited a stationary distribution, so therefore it must be positive recurrent. So what we have shown is xn bar is irreducible, aperiodic as well as positive recurrent. So now let capital T denote this random variable. So remember that the 2 chains xn and xn tilde are kind of running parallelly. So look at the first time that the 2 chains meet, that is the minimum of n such that xn is same as xn tilde. As always, if there are no such n's, we define the time to be infinite. Now let mu bar be any initial distribution of the Markov chain xn tilde. Claim is under mu bar, initial distribution mu bar, the probability that xn equal to y and t less than or equal to n is no different from the p mu bar probability that xn tilde is y and t less than or equal to n for any y in S. The proof of this is here. If you take any n greater than or equal to 1 and any m less than or equal to n and z in S, you can easily see this, and from this the claim follows by adding over m from 1 through n and also over z. From that the claim follows. So now therefore for any initial distribution mu bar and any y in S, and of course any n greater than or equal to 1, if I look at p mu probability, that p mu tilde probability that xn equal to y, I can always decompose it into p mu bar probability that xn equal to y and t o I less than or equal to n, and the same with t greater than n. Now remember that from what we have just now proved, the first term is same as p mu bar probability that xn tilde equal to y, t less than or equal to n. That's exactly what we proved. And the second term we retain as it is, and now we replace both terms by their upper bounds, which is the last expression. So what we have proved is that p mu bar probability that xn equal to y is less than or equal to p mu bar probability that xn tilde equal to y plus p mu bar of t greater than n. But then reversing the roles of xn and xn tilde in this string of inequalities, you would be able to get this also. But that these two inequalities combined really gives you this. That is, for any initial distribution mu bar for the xn bar chain, the p mu bar probability that the first coordinate of the chain is in y after n states minus the p mu bar probability that the second coordinate of the chain is in y after n steps. The absolute value of the difference of these two probabilities is bounded above by p mu bar probability that t, the meeting time of the two chains, is greater than n. Now fix any x in S, and this result, above result, is true for any initial distribution. So I'm going to take a very special initial distribution, namely the initial distribution mu bar is like this. x0, the first coordinate, starts from x with probability 1, whereas the second coordinate starts with the distribution, and the distribution is the unique stationary distribution pi for the original chain, and they start like this independently of each other. With this mu bar, the p mu bar probability that xn equal to y, because it's only looking at the first coordinate of the paired Markov chain, and another paired Markov chain, the first one starts with initial state x with probability 1. So therefore p mu bar probability that xn equal to y is pxyn, whereas for the second coordinate, the initial distribution of the stationary distribution, so the distribution at time n would be the same as pi y. So that's exactly what we've written. And now applying that to this inequality that we obtain, which is true for any initial distribution, what we get is pxy super n minus pi y, absolute difference between these two, is bounded up by p mu bar probability that t is greater than n. This is true for every x, every y, every n greater than or equal to 1. Now recall that t is this random variable, the first time that the two pairs meet. Therefore, in particular, for any z, t is less than or equal to the minimum of n when xn bar is z comma z. Fix any z, so this is equal to this, which is the hitting time of z comma z by the paired Markov chain. Because the paired Markov chain has been shown to be irreducible and recurrent, it follows that p mu bar probability of tzz is finite, that probability is 1, whatever be the initial distribution mu bar, which in particular implies that for any initial distribution mu bar, t is also finite with probability 1 under p mu bar. Equivalently, that the tail probability that t greater than n goes to 0 as n goes to infinity. From that we conclude exactly what we wanted to show, that pxy super n minus pi y goes to 0 as n goes to infinity. This is true for every x, every y in S. So what you have seen in this is two major concepts were defined. First of all, we saw that if you have an irreducible Markov chain, in either transient or null recurrent case, there is no question of any limiting distribution. Whereas for the positive recurrent case, again, if there is a stationary distribution, of course there is a unique stationary distribution. If there is a limiting distribution, then the limiting distribution has to be free of initial distribution, and the limiting distribution for every initial distribution has to be the unique stationary distribution. But the issue is that always the case? What we saw is no. That depends on another property of the irreducible positive recurrent Markov chain, namely periodicity properties. So what we proved was, we introduced the notion of periodicity of a Markov chain, and then we saw that if a Markov chain has periodicity 1, which we normally refer to as aperiodicity, so for aperiodic Markov chain, which is irreducible as well as positive recurrent, there is a limiting distribution. In fact, there is a unique stationary distribution, a unique limiting distribution, which happens to coincide with the stationary distribution. So naturally, it left us with the question of what if an irreducible positive recurrent Markov chain is not aperiodic, deperiodic for some d greater than 1. Well, we don't have limiting distribution in that case, but we were able to prove some analogues of the ergodic theorem for aperiodic case.